Okay, the recording started. Yeah, please go ahead to start. And
Okay.
please introduce yourself first to the audience. Thank you.
Okay, sure. So I'm Chetan Mishra. I work for Dominion Energy in their Synchrophasor group. We formed this group back in 2019, and our goal is to essentially, so we store Synchrophasor data forever. And what we wanted to do is instead of taking an operator room approach, we are trying to use Synchrophasor data to investigate and diagnose issues. So if there is it can range from trying to improve an existing model of some asset to trying to understand from measurements what exactly a particular device is doing, and we do all ranges of engineering analysis kind of work with measurements. So this and I did my PhD from Virginia Tech in 2017 on transient stability, and now I'm in a small signal stability world because we're mostly in small signal space in real operation. So what I'll be talking about today is so back in June of 2022, we had an oscillation emerging from a data center rich region, and it was preceded by some local outages in the area. And what we wanted to figure out is can we diagnose what went on, right? Is it an oscillation that came out of nowhere? Did we have a chance at anticipating it? Before getting into the case, I'll give you a brief on Dominion Energy's footprint. So we have 6,600 miles of transmission. We're basically, we operate in Virginia, and then we also serve parts of North Carolina. And from measurements point of view, it's not there on the map, but we essentially have synchrophasors on all our substations. So ranging from 500, 230, and 115 kV level, we essentially have synchrophasors everywhere, and we have it them in the form of digital fault recorders, and then we have protection like relays. Both of them serve the synchrophasor, or they provide synchrophasor data. And back in 2019, Dominion started to store the data forever. So we have this platform called Predictive Grid, and we store it. It stores all of the synchrophasor data everywhere. So we're pretty much covered from the point of view of observability, and then that's what we have been leveraging to develop approaches to diagnose issues in the system from measurements.
Hi, Chetan, can you hear me? Yeah, it looks like we lost him. Yeah, let's wait for a few seconds to let the presenter rejoin again. I will send him an email. Oh, good.
Yeah, it dropped. It dropped in
No
between.
problem.
But
Yeah.
let me share it again. I'm
Sure.
joining from the web browser because we're not allowed to install Zoom, so I have to.
Yeah,
Okay,
understand.
it's a bit unstable connection to go with the theme. Okay, 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 good. So, because we're talking about data center oscillation today, a particular oscillation event, it'll be good to know why is this problem there in Dominion system. So, what has essentially happened is that in the last 5 to 10 years, we've had a steep growth in data center load, and then today, data center load makes up 15% of our total load or of our peak load. And the challenge with data center is that data centers are coming in one small part of our system. So, and we're running out of transmission to provide or to supply the data centers, and that is coming up with its own challenges because we have limited transmission, and then the data center load is concentrated in a small region. We don't have enough controllers, like we don't have synchronous machines in those regions or no nearby synchronous machines. So it's becoming very challenging from the point of view of having a stable grid. So if data center controllers begin to act, it's difficult for us to really do anything about it, and which is what takes us to the event I'll talk about. So as we are as more and more data center comes up, and then we have less and less synchronous machines. We're having this issue around a lot of local control problems, and the one we'll talk about today is one of those problems. So an issue that comes out of, you have a controller in your system, and then it's not modeled, so you have no idea what it is. And then you take some outages in the system and you start having oscillations, and you don't know how to get rid of them besides shutting down the device, like locating the source in the device. So let's talk about the event we want to talk about today. It's so back in June 2022. So here is what happened in this particular oscillation. So back in June 2022, we removed some hydro units which were close to a data center rich region. It's mainly 115 kV network, so it's not a you would say it's not a tightly coupled, it's not a strong grid in that part of the system. So we took hydro units offline, and as soon as we took some hydro units offline, we started seeing oscillations which were around 14 to 15 hertz, and they lasted for a full 2 hours. And then after 2 hours, the system is changing, and then after 2 hours, the oscillation suddenly vanished. So there were some coincidences in this, because the 5 minutes before the oscillations vanished, someone had changed reactive power set point on a nearby statcom. So people thought that maybe statcom saved us from this oscillation, or maybe statcom had a role to damp this oscillation, which it's difficult to establish given there's a 5 minute difference between when they changed the operating point and when the oscillation vanished. So the goal of our study was to understand where did it originate from. So localization, obviously, is it the data center or is it us? And then more importantly, could we have anticipated this problem? Or is it one of those cases where suddenly some unmodeled dynamics show up in your measurements that you never saw before, like a force oscillation, and you have no idea where it came from? And then you have to do a root cause analysis to figure out. So what we wanted to figure out is, was there some dynamics we could track in the data so that it could have told us whether this oscillation is about to happen? So was there any critical behavior behind it, any precursor to these oscillations? And that was the goal of our investigation. The region I'm talking about where the oscillations were seen first, so they were noticed based on, there were substation lights were flickering in one part of our system. So that's how it was brought to our attention that there's an oscillation going on. The region I'm talking about is these three substations. You'll see D1, D2, D3, data center region. There is some nearby solar, but it was also night time at that time. And then there's a so this is a 115 kV network, which is marked by black lines. And then there's on the 500 kV network, we have a statcom, which is at substation A. So electrically is a bit far from this location because given that it's all 115 kV network. And the hydro units that we took out that triggered oscillations were at substation K, which is here. So we took them offline, oscillations started. And we have pretty much decent coverage in this part of the system. You can see how we have PMU data at the substations where data center is connected, and then we also have it at neighboring solar, and actually even at statcoms and hydro. Okay, so the overview of the analysis is, we'll start by characterizing, so that can help us localize the oscillation, what frequency it is and which location saw it, etc., etc. But more importantly, can we find precursors to this oscillation? What is the nature of, or what is the mechanism behind this oscillation? So I don't need to go into like time frequency representation, but I'll briefly talk about it. So in this particular event, you will notice how there are certain things that only show up for brief periods of time. So we have the oscillation, which is there for 2 hours, but there will also be certain dynamics that will show up for brief period of time. So we need to have a good time frequency resolution trade-off. So evaluating or analyzing the same window of data through a spectrogram gave us some additional insights. And so it's important to understand how to read that picture, right, or how to read a spectrogram. So we'll see certain high energy portions on the spectrogram, and we'll try to understand what they are. So first, starting with the spectral characterization. So, okay, the oscillations were first seen or majorly seen in voltage magnitude. So I picked up voltage magnitude from that region. I picked up the data center bus to begin with. I don't know if it's there or not, if the source is there or not, but the data center substation definitely saw the oscillation. So at peak voltage magnitude, we pick up a pre-event ambient period and then during the event, just to contrast the spectral characteristics of voltage magnitude. So what you'll notice here is the pre-event spectrum is given in black, and then the during event window is given in red. So the main contrast, or if you want to contrast the two spectrum, the main difference is essentially what is happening on the higher frequency range. That's one of the major differences between the two spectrum. But there is more to it. There is also certain changes that you'll see in this higher frequency, like 10 to 12 hertz range. There's a hump here in the pre-event period, and you don't see those dynamics during the event. So this particular component will play a key role in explaining what this oscillation is from or where it's from. We also checked with point on wave data because obviously the oscillation is very close to our Nyquist. So we wanted to make sure there is no aliasing problem, whether this is genuinely a 14 to 15 hertz or 14.7 hertz to be precise, whether it's a 14.7 hertz oscillation, or is it something else just aliased at 14.7 hertz. Keep in mind over here, it's important to mention that we have synchrophasor data reporting at 60 hertz, but we downsampled to save storage. So someone decided we should downsample to 30 hertz. So our Nyquist is around 15, but the dynamics from 50 to 30 hertz are still there. So they could alias, because of aliasing, they could show up at another frequency as well, and we wouldn't know. So that's why on the top right, I've plotted waveform data spectrum. So our waveform data triggers every time an event happens. In this case, it triggered as well. If you look at the spectrum, you'll see obviously the peak at 60 hertz, right, which is where our system is operating. But then you'll also see the side bands, the symmetric like side bands corresponding to the 14.7 hertz oscillation. So 60 plus minus 14.7, you can see those. That means the oscillation is indeed at 14.7 hertz. It's not at a different frequency. Okay, and another clue to gather from this particular event is when this oscillation is happening for 2 hours, it is responding to operating characteristics of the system. What I mean to say is that if you look at the DC part or the slow part of the voltage magnitude here, you'll see how when we took the generators offline, the voltage went down because they must be supplying reactive power. And then you'll see how over a period of 2 hours, you'll see a trend in voltage magnitude. So however the operating conditions are evolving, your voltage magnitude is evolving or increasing in this case gradually. And this particular oscillation is essentially responding to that operating condition, means this particular oscillation's characteristic is a function of where we are operating, which is usually very commonly seen in even control created oscillations, the oscillations that are not feed forward but have a feedback component to them, so that they respond to the grid conditions. So a small clue, but something to not ignore. When we're investigating, we have to gather all clues around the oscillation to figure out what's going on. Okay, and then for mode shape itself, so what is the nature of the oscillation? If you look at the spectrum for reactive power and real power on all the lines in that region, so there are no synchronous machines locally in that part of the system. So essentially, the way the solars are, or the way how the PV plant controllers are designed, is that there's a pretty good decoupling between P and Q. So in the past, when we have ever had any issues or any oscillations in solar plants, you will see how if an oscillation comes in reactive power, it's a volt-var type of oscillation. You'll see the real power not even seeing that particular oscillation. It's a very good decoupling between P and Q in the way the controls are designed for our PV plants. So there is no reason that if a PV plant sees a voltage oscillation, its megawatt starts oscillating. It's we have never seen a case like that in our system. So even if something were to start as a volt bar oscillation, the challenge always is that when will it turn into a megawatt also, and it all depends on frequency response of individual devices. In this region, there is no device that will lead to that. So if you have a start with a voltage oscillation, in this region, there is no neighboring device that might turn it into a megawatt oscillation also. So in this case, what you'll see is that it's predominantly VAR type of problem, and it's mainly seen, that's why, in voltages and VAR, and not so much in megawatt consumption of this particular data center load. So volt VAR kind of issues. And that means that it tells us what to chase when we are trying to localize. And for localizing for this case is relatively easier. First of all, it's in 14 hertz range. There is no local dynamics to resonate with this 14 hertz, at least not that we know of from ambient conditions. But also, so what we do is we chase the volt and the var relative participation of different parts on the network to localize the oscillation. So what you'll notice here is that for the top shape or oscillation shape or mode shape or whatever you want to call it, the top one is for reactive power participation of different lines in this part of the system. And then the bottom one is the voltage magnitude participation. And what you'll see is that voltage, the data center bus has the maximum voltage magnitude participation in this particular oscillation, and also the maximum reactive power. Furthermore, the reactive power and the voltage magnitude are nearly in phase. So that kind of gives you a clue on this must be feeding the oscillation. Uh, and okay, so we start with, okay, so the problem is them and not us. So what we do now is, okay, so if the data center is the problem, why did this oscillation happen? Is it a forced oscillation? That's always the question to ask. Like, because if it was a forced oscillation, that means there is really no chance for me to anticipate whether this oscillation will happen or not if it's something very internal to a device. So to understand the underlying mechanism, what we noticed is that there is no, so first of all, there is no, the oscillation is at 14.7 hertz, but there is no other dynamics around 14.7 hertz. The only other dynamics in that frequency range is the one that is around 10 to 11 hertz. Now, there is something interesting about it. In this particular event, if you look at the spectrogram of voltage magnitude at the data center bus, what you'll notice is that there are these blips which are labeled as A. So there are these bursts of energy happening again and again around 10 to 11 hertz. And as soon as the oscillation starts, which is the period B, these vanish. So do they have a relationship with each other? Do these two dynamics, like does this A, these blips at 10 to 11 hertz, do they have anything to do with the oscillation? But more importantly, why do we see these bursts of energy every few seconds or every few minutes? Why do we see these bursts of energy? That's something to explain as well. Okay, so what we did is we went to historical data and then we collected all the oscillation events in 14 to 15 hertz, right? And it was fairly easy to do it because that range has no other modes or dynamics. So detecting an oscillation in a frequency band where the spectrum is relatively flat is not that hard. So in this particular case, what you'll see is for visual representation, I've plotted the collection of points. This is 1 year of data leading to the oscillation. So here I've plotted the collection of points you'll see in C. These are where the oscillations are. So this plot, a 2D plot, one of the axes is power or log of power in the signal in 14 to 15 hertz, and one of the axes is the y-axis is log of power in the overall signal. So whenever there is a higher concentration of power in the signal in 14 to 15 hertz with respect to the overall power of the signal, that's where you will, and then I catch it as an outlier. So when we do that, there were 10 similar events, but all 10 of the oscillation events happened in the same week. Now, why do we care about past data? Is because when you're trying to explain or when you're trying to infer anything from measurements, it's always good to have enough evidence in support of your narrative. Inference is weak if we rely on a single event and then try to extrapolate, given we don't have models to guide our thought process, right? So luckily I found 10 similar events, again 14 to 15 hertz. And in all of those events, so I've plotted on the right, I've plotted three of those events. And some events lasted for as little as 2 minutes, while the longest one which we caught was 2 hours. What you'll see here on the left is the first column is time domain plot of voltage magnitude at the data center. These are the detected event windows. And then the right side is the time frequency. So the same signal in time frequency plane, but I've zoomed into 9 to 15 hertz range, the higher frequency range. So what you'll see here is in all of those events, there is some dynamics around 10 to 11 hertz showing up as periodic bursts of power, and then they will lead to an oscillation, and during the oscillation period those dynamics vanish, which is common to all of these plots. So that means that this phenomena of one particular dynamics leading to the oscillation is common to all the events that we have seen, all similar events in that location. Okay, so now the question is, why do we see bursts of energy in here? Like, I mean, it would be something else if it would be a normal thing if you saw a mode in ambient data and then you see oscillation. That's very normal. But here you're seeing bursts of energy, or a burst, increase in signal power momentarily. So if you zoom in and if you look at time, the same data in time domain, what you'll notice is that the data, this is the stable period before oscillation. What we'll see here is that you will see on top of every second precisely, there is a sag in voltage, and it's followed by a ring down behavior. So apparently what is going on is that there is a periodic transient every second, right? That is perturbing your system, or it's exciting your system. And then you're seeing the impulse response of the system in the form of this ring down data. Now, this particular ring down data, if you look at it through a mode estimation lens, this yields a mode in 10 to 11 hertz range. That means that in this particular system, there must be some kind of periodic forcing in this part of the system, which is exciting this particular 10 to 11 hertz mode. Now, why is this there a periodic forcing? So what we have seen in our system is that a system like, I mean, any real world system is full of harmless periodic components, and a lot of times they might be confused for oscillations or force oscillations, but a lot of times they are controlled inputs. One of the examples could be a load duty cycle. Like a load might have that duty cycle forever, and it has a periodicity associated with it, or maybe a weekly periodic behavior. It's there in your system and it's controlled in size. It's not born out of instability. So in this particular case, in this case, we have a voltage sag that's happening once a second, but we have analyzed more such voltage sags in other parts of our system as well. Some of them were so tiny that they don't really create any power quality issues. One of the ones we analyzed a while back or years back was a voltage sag that happens once a minute, and we could locate the source to be outside our system. But in this particular case, this particular voltage sag is happening every second. So it's different from the every minute voltage sag for sure. So there are multiple voltage sags we see in our system all the time. So there is a periodic excitation on the system, that excites some dynamics, right? Which is the setup for this part of our system. So where did these periodic excitations come from? So if you try to track the source of periodic excitation, this particular one is the data center itself. Data center has the maximum participation in these periodic voltage zags. So essentially what is happening is data center has some process in there which is precisely happening on top of every second, and then they are kicking the system, and it allows us to see some behavior, or see the impulse response of the system from that point. Now, when we ask the data center owner, so they don't really cooperate when you want to investigate things. They don't really tell you what is connected, what they are doing. But they were kind enough to tell us that what is essentially happening in the data center is that they do some sort of data processing on virtual machines, which is timed to the GPS clock. So once a second precisely is where you'll see a processing power spike, which creates this voltage sag every second. And it happens perfectly on top of every second. So now if you think about our setup, we had the oscillation, but then we also have the data center that is exciting the system. And then there are these 10 to 11 hertz dynamics which appear stable, but they vanish during oscillations. Okay, so then let's analyze these 10 to 11 hertz dynamics, because they always vanish whenever oscillation starts in all the 10 events that we saw. So what we did is we picked up periods that led to an oscillation. So in all of the events, all of the 10 events, we pick up this period leading to the oscillation. The excitation is happening every second, means you have a forcing input more like an impulse every second. So we took this window of data, we chopped it into sections of less than 1 second, and they are non-overlapping segments, essentially to estimate the ring down mode, right? Or estimate this dynamics that are triggered when every time a transient input happens. So when we plot the mode in damping ratio and frequency plane, what you'll notice is, so I've plotted the trajectory of the mode as I'm estimating it using these 1 second windows, right? The windows start at the ring down stage, right? What you'll notice is that in all of the cases, the mode changes a bit. So every second, right, like as you're going from left to right in time, the mode's characteristics are changing, and its damping is also reducing. And in all of those cases, the oscillation starts with this mode becoming zero damped or negatively damped, however you want to call it. So that means that the setup is I have this 10 to 11 hertz mode, which is only visible when data center calculates something once a second. It excites the mode, it enables us to study it. Otherwise, the mode is so stable that you can't see it in ambient data. But then once the data center excites it, we can estimate it. And if we estimate it, we track the damping of this mode, the mode destabilizes into the 14.7 hertz oscillation, right? So now what's the most likely mechanism? Why did we end up with an oscillation? So first thing to think about is that if you look at how the oscillation progressed in all of the 10 event cases, but let's focus on the event right now at hand. The way the oscillation progressed is that for 2 hours, the system was changing gradually, as you can see, following its normal route, right? And then the oscillation vanishes. It's similar to, so one question to ask is that once the mode became unstable, right? How was it able to come back to the equilibrium? And this essentially happens if your in your if your motion or your trajectory in state space is at least bounded, such that it can be restabilized, right, from a local stability point of view. So it has to have it has to have a bounded motion during all of those 2 hours. It should not, you can't expect some state variables to fly off to infinity, because 2 hours is a very long time and we're talking about dynamics that are unstable. So you can't expect some internal state variables to fly off to infinity, and then once the system becomes small signal stable, it comes back. Highly unlikely. So the trajectory must be bounded. Now, if it is bounded and we are seeing this periodic motion, then is it Hopf bifurcation? Because we have a pair of complex eigenvalues, they cross the imaginary axis, which we saw from data. And then it leads to a limit cycle, which is a stable limit cycle because your system is attracted to it and it's stuck on it. But then the problem is that it's difficult to figure out when the limit cycle suddenly shows up because of a discrete change in parameter. So let's look at the starting time of the oscillation. There were some system parameters, right? Like say operating condition, and we suddenly reduce the ramp down the generators, and as soon as we quickly ran down the generator, the oscillation started. So here, that whole concept of smoothness of this limit cycle creation is difficult to understand by looking at cases where the parameter quickly varies and you have a limit cycle. It's difficult to understand whether there is any kind of smoothness in the dynamics. But let's look at the how the oscillation vanishes in each case. So in supercritical Hopf bifurcation, you generally start from a zero radius. Your unstable equilibrium, your at the moment your equilibrium becomes unstable, it's surrounded by a stable limit cycle at zero radius. And as the parameter continues evolving, the limit cycle can become bigger or respond to the parameter changes. In our case, the limit cycle suddenly came up and suddenly vanished, right? Something that is much more common to scenarios where real world controllers become unstable, which we have seen at multiple of our solar plants, is limit cycles that are born out of unstable controllers coupled with hard limiters. And this is, we have seen it in many solar cases where you take an outage in the system and the volt var control or the AVR becomes unstable at some solar plant, and then because and then it starts bouncing between the limits set on the controller. This is a far more common case in these local instabilities or local controllers being unstable. So and hard limiters are everywhere in real world controllers. So we, for us, we went with this narrative that it's the most likely mechanism. Keep in mind, it's a data only analysis. We don't have a model to recreate anything, right? And this is the best we could guess based on the evidence we collected from measurements. Okay, so now I'll go into, so we're talking about multiple things happening in the system. So let's see if we can create a proof of concept simulation to revisit what exactly happened or the chain of events. So in this case, I'm essentially trying to show how easy it is to create this limit cycle even with a linear controller with hard limiters. In this case, we have a PI controller. It's followed by a hard limiter or a saturation. And then the output of that controller after saturation goes into a system. System I modeled as a first order system, more like a Thevenin equivalent, if you want to call it, and with a small time constant to essentially act like a Thevenin equivalent or act like a quick responding system. So we have a feedback control here, and then there's a time delay in feedback as you would expect normally. And in this case, what we'll study is that if we change the gain of the grid, which is essentially what happened in our case when we removed nearby generators, we'll study how this thing will create an oscillation for us with the help of limiters and an unstable feedback control. Furthermore, the disturbance I'm injecting at that point on the grid, that is a combination of a noise, white noise, Gaussian white noise process, and also a periodic pulse once a second, because we want to mimic what we were seeing in our system, right? So there was a once a second input that excites your dynamics, and then this controller becomes unstable, and you see an oscillation because of limiters. And the critical mode here is 3.1 hertz in this. So I've arbitrarily set parameter values for this control setup. It's a proof of concept simulation. It does not exactly It's not there to match the model or something. It just explains how the chain of events. If we look at this, so while we're in the stable period, right, while the controller is stable, so grid is in stable conditions. If we plot the part spectral density of this output, which is on the bottom right, you will see the effects of periodic impulse, which is these spikes in the spectrum every 1 hertz. And then you'll also see the critical mode dynamics at 3.1 hertz, which we can see as a hump here. So, a thing to think about is that there is a combination of inputs and autonomous or like response of the grid to the inputs, and it's very important to distinguish between the two. Right? These are not two additive oscillations, but or they are not two additive dynamics, but one is driving the other. So it's important to keep that in mind. Okay, so now what we'll do is we'll make the controller unstable. So we increase the gain of this grid, which is kind of mimicking a more sensitive grid, right, or a weak grid. So as we increase the gain of this of the grid block here, what we end up seeing is that we'll have oscillation, or we have actually the feedback control becoming unstable. But then now we are plotting the phase portrait, or in the uy plane we are looking at the trajectories with and without limiters. And what you can see here is that it's fairly easy to create a closed loop or a periodic motion when you have hard limiters interacting with an unstable controller. On the top right, the same instability without any hard limiters, and on the bottom right, an instability with hard limiter. And you can see how the hard limiter will chop off the phase portrait or state space in a way that you get this cyclic motion, or you get a closed loop or a limit cycle, obviously a non-smooth one. Okay, so now we know that there's a 10 to 11 hertz mode that's local to the data center, becomes unstable, leads to an oscillation combined with the limiters, or resulting with its interaction with the limiters. So now let's track what happened. So could we have anticipated this issue? So we're talking about how we have oscillations that suddenly came up. Could we have tracked this? We know what to track now is the 10 to 11 hertz mode. So I'm plotting here is the signal power in 10 to 11 hertz range, and I'm plotting it along with the signal power, voltage magnitude signal power in 14 to 15 hertz range. And what you'll notice here is this is 1 year of data. And what we see here is that the black is the signal power or the critical dynamics behind the oscillation. Whenever we took local outages in that region, you will see an increased power or relatively less stable 10 to 11 hertz mode, which is expected. But the thing is that that means we could have gathered these clues in the past. Whenever there were outages, there is a 10 to 11 hertz mode that becomes relatively less stable. But what is interesting, what we could not explain was that in the 3 months leading to the oscillation week, you can see how there is a gradual increase or a gradual deterioration in stability of the 10 to 11 hertz dynamics, right? We have a 10 to 11 hertz mode, but then it gradually becomes worse. And towards the end is where you start seeing oscillations, which are given by these vertical peaks in the red plot. Red plot is the power in the signal in 14 to 15 hertz range. So you can see how this is gradually increasing, and eventually you see oscillation, which tells us that when we saw this oscillation, we almost had 3 months to track an evolution of a particular mode, and we could have taken decisions on time as opposed to waiting for the system to tell us when to, or as opposed to being reactive and solving it as a root cause problem. Okay, this problem is very common to Dominion, so this is not an isolated incident. Unstable controllers during weak grid, uh, this is so common in our system, and the reason is because in practice there is a set it and forget it mentality around controllers, right? Like when a facility interconnects to our system, right? there is no rigorous testing. Like, we don't test it against a range of operating conditions. Now, imagine having devices like that in the system, and then you take some outages, and the oscillations or the instabilities reveal themselves, and that is happening very commonly in our solar plants. And in this case, we saw it in the data center. Now, the problem or the thing that makes all of this challenging is that there is inadequate modeling. So you can't really anticipate these problems, right? You can't study what if scenarios. There is absence of models for assets that utility does not own, and even for assets that we do own, often we have found missing components or average dynamics. So there is a case I was studying recently where there was a nuclear plant, right? So it's an old nuclear plant, and we were trying to do understand the model response or validate the model in the correct language, and it had some missing 7 hertz dynamics missing from the PSSE model, and the 7 hertz dynamics were very poorly damped, and we saw it each time a fault happened close to the plant. So there will always be missing components. There's another case where in a lot of our solar plants we don't have time delays modeled, like feedback delays, and we have found some solar plants where they even have feedback delays of 10 to 15 seconds, right? So imagine what instability issues that creates. And on top of that, these are not modeled in the traditional model. So whoever is studying using models to take these major decisions, they will be blind to these events. So now, since I'm talking about data driven analysis, it will be important to mention what exactly is the complication about data only analysis. Because if you think about it, all the investigation we did in this particular case has no models to guide yourself. You're using measurements, then you're collecting more evidence from past data to arrive at a conclusion. Now, the problem is that a lot of real world controllers could have structural changes which are difficult to study, or which are difficult to infer when doing a data driven investigation. So, one example case is on the bottom right, I plotted a spectrogram of reactive power output of a particular solar plant. And the solar plant, you'll see how wherever you see these bright red regions is where there's an oscillation, but the mechanism behind this oscillation keeps changing. So in early periods, it's trying to do a power factor control. So there's an oscillation resulting from a power factor control, but then it stops doing power factor control in between, so you don't see any oscillations. And then suddenly it switches to voltage controller. Voltage controller is unstable in this time period, so you start seeing oscillations in volt because of unstable AVR. And then followed by that, there is a long period where the voltage movements are within the dead band, so the controller is not doing anything, so you don't see any oscillations. Essentially, the unstable behavior doesn't reveal itself during that period. So all these, imagine if devices are operating like that, how difficult it becomes to infer what the system is trying to do if it's internally structurally changing. And we're talking about assets we have no idea about at times, as to what their purpose is, or what exactly is their default behavior. So the data driven analysis always has these risks, right, in inferring something about the system. Okay, that's pretty much it. To summarize, we have we looked into a 14.7 hertz data center oscillation, but if you look closely, it wasn't a force oscillation, or it was from a natural, like a control mode local to data center that became unstable. But we could only study, or we could only make this connection because data center also is a source of exogenous excitation that excites this particular mode, which enables us to study and track it. Otherwise, it's so stable that we can't really estimate it from ambient data as well. And then we saw it progressively getting worse from the point of view of stability over a period of 6 months, and then we saw oscillation, which means that there was actually a chance at anticipating this particular event. With that, thank you, and if there is any questions, please feel free.